Hello, and what's up? Today, I will look at the WwiserR built-in distance culling systems, aka the bread and butter for massively improving performance when integrating Wwise into the Unreal Engine. Let's start by looking at how the WwiserR sound emitters are organized. At the core of each sound emitter sits the SoundEmitter Component. Derived from it are the standard SoundEmitter Component and its child classes for specific use cases, such as the AuxSoundEmitter Component we've seen in previous videos. On the other side of the spectrum sits the StaticSoundEmitter Component, which is centrally managed by the StaticSoundEmitter Manager, and intended to use for looping sounds that come in large numbers, and play on static actors, such as trees, lights, torches, and so on. In this video, I'll break down each of these components, how they work, why, and their impact on performance, by measuring in Unreal Insights. As we've seen in the first video in this series, my main performance concern when integrating Wwise into the Unreal Engine are idle AK components. Therefore, the entire WwiserR distance culling system is based on only spawning AK components when their owning sound emitter is relevant to any sound listener in the scene. To clearly understand how this works, it's important to know that WwiserR explicitly distinguishes one-shot versus looping sound events for several reasons. As we'll see in this video, doing so facilitates distance culling. Secondly, it saves development time by eliminating the need to create separate stop events in Wwise for each looping sound in your project. In doing so, it also declutters your Wwise and Unreal projects, and the amount of assets and data in your project content folders. More importantly, by embodying the single source of truth principle, it reduces the risk of creating bugs by accidentally pointing play and stop events to different parts of the Wwise actor mixer hierarchy. That said, let's look at each of the components in the WwiserR sound emitter hierarchy. The SoundEmitterBase Component, which is not accessible in blueprints, acts as a wrapper around the AK component. As such, it makes sure we only spawn an AK component when we need it. It also handles the basic distance culling properties and functionality, exposes one-shot Wwise event functions, and tracks any Wwise game syncs posted on this emitter, so that any game sync is properly remembered and posted to Wwise whenever we do spawn a new AK component. The SoundEmitter component does get exposed to blueprints, and before looking at how it handles distance culling for looping sound events, let's see how it deals with one-shots. When posting a one-shot on a sound emitter, WwiserR simply checks whether a listener, or rather its distance probe if it has one, is within the attenuation range of the posted event. While this works perfectly fine for 99% of the cases, this might eliminate some longer and louder sounds if the listener finds itself just outside the attenuation range when the event is posted, but is moving towards the sound emitter as the sound is playing. To counter this, we can add a buffer on the post one-shot node to extend the range within which the event should post. If however it's possible that either the emitter or listener teleports during the event, for example when the player respawns, or switches between characters, it's also possible to ignore the distance culling system entirely, either when posting the event or directly on the sound emitter itself. It's worth noting that even in this case, there might still be a large performance gain, as the system will still eliminate the idle AK component before and after the sound is playing. Now, let's see what this means for performance by spawning 144 non-playable bennies, doing their non-playable benny things. Without any culling or voice limiting, we can see that the AK audio engine is eating between 90 and 135 milliseconds of CPU time per frame, and rendering between 150 and 320 voices. Of course, we can reduce this by voice limiting our footsteps and barks in the Wwise authoring tool. Indeed, the CPU load now fluctuates between 25 and 45 milliseconds while playing 10 to 20 voices. Obviously, WwiserR can do better. Let's turn off the Wwise voice limiting and enable the WwiserR distance culling instead. We have now reduced the CPU load by about 90% and the voice count to about 1/3 compared to the original scenario. As the footsteps are rather quiet and short sounds, it's safe to assume that, while they have an attenuation range of 70 meters, their actual audible range is closer to 40 meters. Therefore, I'll reduce their culling range by setting a negative buffer of 30 meters on the post-footstep event node. By introducing this optimization, we now have a CPU load between 3 and 7 milliseconds, with a voice count of up to 40 voices. Beautifully enough, the Wwise voice limiting system feeds back into the WwiserR culling system. So, if we turn on the Wwise voice limiting again, on top of the WwiserR culling system, the CPU load drops even further to between 2 and 5 milliseconds per frame, with the same voice count as when we were only using the Wwise voice limiting system. Of course, this must come at an overhead cost for the sound emitters, right?
We should split up.
Indeed, as we can see in this scenario, the SoundEmitter component adds about 2.5 milliseconds to the CPU load. However, a big part of that is caused by the visual debugging. Turning this off shows us that the actual overhead is less than 1 microsecond per emitter. It's also important to realize that with the default Wwise API, the CPU cost will keep scaling up as your project grows. However, with the WwiserR culling systems, the CPU cost remains very much constant in relation to what you actually hear, regardless of the size of your project.
I swear we closed this sprint last week.
Moving on to looping sounds, the WwiserR SoundEmitter component handles looping sounds distance culling, exposes functions for posting loops to blueprints, and tracks game syncs specifically posted on playing IDs, as these change when loops are devirtualized in WwiserR and reposted to Wwise. The obvious way to distance cull looping audio events would be to continuously compare the distance between the listeners and the sound emitter on which the loop or loops are posted. The WwiserR distance culling system, however, is entirely event-based and therefore far more efficient. In fact, with one specific exception which we'll see in a moment, WwiserR sound emitters never tick, except when necessary for visual debugging. So how does this event-based culling work? When a loop is posted on a WwiserR sound emitter, WwiserR checks if the distance between the emitter and any listener in the scene is within the attenuation range of the posted event. Accordingly, it either posts the event to Wwise, or virtualizes it, meaning it keeps track of the event without actually posting it. At the same time, it calculates the earliest possible time that the emitter can reach the critical distance. It estimates the attenuation distance of the corresponding event plus the buffer set on the post loop node. It then selects the earliest calculated time from any of the looping events posted on the emitter. When that time is reached, it will repeat this process, and virtualize or devirtualize the corresponding loop if necessary. As a result, distance culling happens more frequently when the emitter reaches the critical distance to a listener. However, as the difference between this critical distance and the emitter to listener distance increases, the frequency of culling passes rapidly decreases. Additionally, an emitter updates its next distance culling time when its maximum speed has increased or the emitter has teleported. Similarly, all emitters on which looping audio events have been posted execute a fresh distance culling pass when a game world listener is added or any listener has teleported or increased its maximum speed. For this to work, WwiserR needs to know the maximum speed at which each sound emitter and listener can move. There are several ways for the user to tweak these, even at runtime. On the emitter side, we can set whether the emitter can move altogether. If it can, using the Auto Emitter Max Speed option, will automatically calculate and update the emitter's maximum speed. For this, however, it will tick as long as the emitter is moving. As said earlier, this is the only case in which a WwiserR sound emitter ticks, except for visual debugging. With this option selected, it's also possible to reset the maximum speed to 0 as soon as the emitter stops moving. As the default option, using the auto emitter max speed guarantees that the culling system always works correctly, eliminating any risk of user errors, at the potential cost of slightly increasing the CPU load when many emitters with looping sounds are moving at the same time. In such cases, it's advisable to manually override the maximum speed. Finally, when an emitter is moving relative to its parent actor, it's possible to use the parent's location as reference for the culling system, to reduce the frequency of distance culling passes. Of course, all those parameters can be adjusted at runtime to best accommodate for specific gameplay conditions. The maximum speed for the listener is manually set in the Listener Manager settings, and can be overridden at any time via blueprint nodes. When the listener target is a character, the listener maximum speed can also automatically adjust to the character movement component. In this case, a lower threshold can be forced by selecting the corresponding movement mode. This can help spreading out distance culling passes on different components if the character movement mode changes frequently. Now, let's check in with our beloved Bennies again, joined by their boisterous bearded besties after a balanced blissful bona fide brunch break, and see what all of this means for performance. We now have 400 buzzed and brightened bonitos playing a single loop each. Without any wise voice limiting or WwiserR culling, the CPU load fluctuates between 80 and 150 milliseconds per frame, while rendering 400 voices. Limiting the wise voice count to 12, reduces the CPU load to 35 to 60 milliseconds, with 12 physical and 388 virtual voices. Using the WwiserR culling system instead, the CPU load drops to between 9 and 13 milliseconds, with 10 to 26 physical voices playing. Combining voice limiting in WwiserR with the WwiserR culling system, we're saving another 2 milliseconds, with 12 physical and up to 16 virtual voices. Finally, the AuxSoundEmitter component uses a very similar culling system to override the SoundEmitter's culling systems when any of the aux buses connected to the emitter are relevant to a listener in the scene. It also exposes aux bus related functions to blueprints, and tracks connected buses and their respective world listeners. So, to wrap up this video, let's see all of this work together in our scene from the previous video.
Time to show these bad guys why I should stick to video games. Don't worry, guys! I'll just shoot wildly. It always works in the movies. At least the enemies are consistent. They always show up uninvited. Friendly fire? Just practicing my aim. Oops. If anyone needs me, I'll be over here, not getting shot.
That's all for today. Next time, we'll look at how the StaticSoundEmitter component can help create detailed environments at a very low CPU cost. I hope you liked this video, and as always, any feedback, suggestions, or ideas for further development would be greatly appreciated in the comments below. Thank you very much for watching.